Hi everyone. I'm Alexy Pellegrini from Kitware Europe. I'm a CMake trainer at Kitware Europe, but also a C++ developer. I also do some kind of other stuff on my free time, such as working on an LLVM backend for an architecture created by a friend. And I also do some graphics programming stuff, mainly with Vulkan. Let me introduce Kitware quickly. So we are a company that is mainly based in the US, but we have a European branch in France that has been created in 2010. We work for different kinds of customers, such as academies, but also government agencies, and mainly private companies. Most of our platforms are actually cross-platforms and also open source. We work in different fields, such as computer vision and medical computing, mainly. Most of the code we write ends up in the open source world, even when we are working for a private customer. And we offer different kinds of services, such as training, support, and full development. So the first point is a very quick reminder about CMake. So CMake is not a build system, it's a build system generator. So CMake itself doesn't drive your compiler toolchain. It will only generate a script of a native build system that will then compile your project. And the main reason to use CMake is pretty simple. It's just that it's the most used build tool to build C++, and even LLVM is built with CMake. Let's talk about C++ modules from a language standpoint. So the classic approach when we are writing C++ code is to have header files, which contain the declaration and the inline code, and source files for the definitions of our functions. So here is an example of a really complex C++ code. And this is how it is actually used when we use it from another source file. So we use the preprocessor to copy the header in the source file. So the compiler actually compiles the code that is on the right-hand side. So with the classic approach, we have two types of files, which are the headers, which are just never built, and the source files that are actually built that will just copy the content of the headers. This leads to some issues, such as the compile time that is increased because the header content is passed multiple times, once for every include in a different translation unit. There is no encapsulation. Everything that is in the header will end up in your translation units. And also, especially with some system headers, sometimes changing the include order may actually break the code. So C++ modules has been introduced in C++ 20. And the main feature is that it replaces the preprocessor include command with a semantic import of semantic entities of the C++ language. And when you write a module, you will have to explicitly export the symbols you want to have when you import the module. So the preprocessor won't leak out of your module and stuff like that. There are two kinds of module units. There is the module interface unit, so there is one per module, and it's the only required file. And you may have some module implementation units in case you want to split your module in multiple translation units. So here is the same code, but written with modules. So this is an interface unit because it starts with export module and not with module. And as you can see, I explicitly export my foo function. So I can import the foo module in any kind of translation unit. As you can see, my main.cpp isn't a module, but I can still import a module in it. And then I can use the foo function because it has been exported from the module interface. Note that in C++, modules do not create implicit namespaces. So here my function is in the global namespace, so be aware of the one definition rule. To summarize, there are these types of files. So the module interface unit, which starts with export module and a name, it will generate both an object file, if there are some code in it, and a built module interface, which has the extension PCM with the LLVM toolchain that contains the module definition. So that's the file that is used to import a module. Then you got the module implementation units, which starts with module and the name of the module, which generates a classic object file and are optional. We can put everything in the interface unit. And then the traditional non-module units that can still import modules. The built module interface is what is used to import a module. That's an implementation-specific file format that contains the module content. Like, it can contain anything, such as some AST parts or even intermediate representation, and is used to import the module. So this is the summary. So the main issues with headers are solved by modules, such as the build time, because we only build the module once and then we import it as is. The encapsulation is guaranteed because everything has to be exported explicitly. And import order doesn't matter because it's a semantic import, so it doesn't change anything if we shuffle them. But modules created new issues. The first one is that since the dependency is per file instead of per target, the build order of modules has to be more precise, which isn't the case with the classic approach. And also, it tends to reduce the build parallelism due to the stronger dependencies between the files. There are other features in modules, such as partition units, which enable to have some smaller modules in a bigger one. Header units, which are importable headers. That's basically just precompiled headers, but in the module form instead of the header one. And the global module fragment, which is a special fragment in your module where you can use the classic C++, so you can use the preprocessor, you can include file textually and stuff like that. So here is an example of these features. I try to make the smallest example possible. So here, what is important is that when you import this foo math module, you will only see a min function. You don't see the content of windows.h, you don't see the macro nomin-max, you don't see any algorithm because the import is private and stuff like that. So to build module, we need two things. The first one is a toolchain that is able to build modules. We are lucky because Clang 15 supports the main module proposal, which is the first paper. So this is the paper that defines most of the module semantics and how does it work. And most of the papers are just mainly defect reports or just clarifications about very specific stuff. We also need another tool that has been added to LLVM 16, which is Clang Scan Depth. This is a command line tool that will scan module files to generate the dependency list of a module without parsing the whole file as Clang will do. It outputs a JSON file to specify all the dependencies of a module that uses a format that is specified by this paper, so the 1689. This paper has been submitted by Kitware, by Bill Hoffman and Ben Boker, I guess, and every toolchain implements it. So GCC and MSVC outputs the same JSON files. Small reminders about a few CMake concepts. The first one is the usage requirements concept, which is related to what we call modern CMake, which is the way we write CMake code since the third version of CMake, CMake 3. So the goal is to have a more target-centric approach where we assign properties to targets, and then using target links libraries, we will propagate those properties or not, instead of having a directory-based approach where targets get properties from the directory, and this has the main advantage is that the order in which the targets are defined doesn't matter, the structure of your project doesn't matter, and stuff like that. So there are some scope for properties. So a property can be private, so it only affects the targets that get the property. It can be interface, so it only affects the target that consumes our target, or it can be public, and then it's both. There are also the generator expressions, such as build interface and install interface, which may change the behavior depending on if we are building the target or consuming it from an install tree. Another concept we need to build modules are the file sets. So the file sets, which are defined using the target sources command, is a new way to assign sources, to add sources to targets. And we can create file sets, so it's just a file bundle which has a type, so it can be either headers or STEG6 modules, and it also has a name. We also need to enable C++20. So you should use the compile features instead of the CMake STEG6 standard variable. So you have the target-centric approach, and if anyone consumes this library, it will automatically get the right flag instead of having to redefine the variable in every project. So the modules can be built with MS-Build or Ninja. There is no Makefile support, so you should use Ninja. So I have two modules, X and Y, and X imports Y. If I try to build these modules using the classic CMake approach, so I give the sources to add library and then enable C++20, it may fail, depending on your luck, because the build order isn't guaranteed to be respected. So if X starts to be compiled before Y is compiled, then it will fail to import the module, because we need an artifact generated from Y build, which is the BMI, to import it in X. So instead, we will use target sources to define a file set that has the STEG6 modules type, which will change the generated Ninja script. And what this script will do at first is to use Clang Scan Depth to scan each module file to generate a DDI file, which is a JSON. And then for each target, all this DDI will be merged into a single DD file. And the build system will use this DD file to know in which order each file must be built. So here, it will know that Y must be built before X. So Y will generate the object and BMI, and then X will be able to import Y using the BMI. So the BL output will looks like this. So as you can see, there is the scan step, then the collate, and the build of the modules in the right order. And for the verbose output, you can see that the scan step is done by Clang scan depths with the right format. And the collate is done by a secret CMake command line -E. So the CMake -E is a cross-platform command line utilities, a bit like Git, that provides some cross-platform utilities like copy files or generate a hash for a file and stuff like that. So this one isn't documented, but it exists. Very small information about importing modules. The problem with importing modules is that the BMI aren't stable. They aren't standard either. So the best way to import modules is simply to install all your interface units like you would do with headers. And when you import this target in another project, you will get this build output. So here I have another project, which is test, that has a main.cpp file. And as you can see, CMake will generate a script that will rescan foo.cppm and also main.cpp, and then collate for each target. And the most important part is the fifth step, which is not a full compilation of the foo.cppm file. It's only a pre-compilation using the precompile flag with Clang. So when you import your target like this, CMake will generate a script that will just generate the BMI of the imported target, of the imported modules, and then link against the pre-built library that has also been imported. So it doesn't rebuild the whole module. And there are some information, some pointers on a few informations. Thank you.
Thank you, Alex. Questions, please.
Hi, thanks for your talk. Question, so CMake makes use of the Clang scan depths program, but what if I'm compiling with MSVC or GCC? Is it still using Clang scan depths?
No, so all two chains supports the scan stuff with CL, which is MSVC. There is a scan option to scan a module, and this is what CMake uses. I don't know for GCC, but there is obviously something to support this.
Thank you. Would it be difficult to extend the support to, or to generalize the support to Clang modules? I'm thinking, could we build LLVM itself using scan depths and explicit modules this way?
I don't think so. I'm not sure I got the question, but switching from the classic approach to modules cannot really be automated, if that's the question.
Yeah, I was thinking about, so LLVM itself is already modularized, but it uses Clang modules, not C++ modules. So I was wondering if it would be difficult to generalize the CMake support to work with Clang modules rather than C++ modules.
I don't think they are related, because the Clang modules are just targets, right?
But we can take this offline. I think they share the same implementation underneath. But,
I don't know, honestly. Sorry.
I have a very large code base I'd like to try this out on. One of the things I'm really interested in is reduction in compile times. there seem to be two obvious ways to do this. Either to go from the bottom up and start by translating my most fundamental libraries to modules and then propagate it to the rest of my code base, or profile my build, find the heaviest libraries, and target those first. Which would you recommend?
Honestly, switching to modules will be a more like breaking change rather than just trying to optimize your existing code base, to be honest.
Yeah, okay. So, bottom up?
Hey, one thing. You talk about dependencies, and then that. When you spread in this in headers, every thread. So if you have like 100 cores, every thread is compiled in the same header 100 times, and this parallelizes really well. But you spend some time doing the same thing. Now, module. If you realize that you're going to compile your module, like one module first, then Amdahl's law makes your build like slower than without modules. So could you compile those modules when you realize that a single module is dependency for 20 other things? You could just compile the same module 20 times. So CMake has an idea of how many threads will be running it?
No. And generally, you will lose more time building 20 times the same thing rather than just building it once and wait for the first build to end. Not convinced. But I've seen some measurements, and what is interesting is that, yes, maybe the parallelism is lower, but most of the time, because each translation unit will be really, really faster, it doesn't really matter. And instead of like increasing parallelism, you can just lower your hardware.
As in removing cores from...
Because you won't need them anymore with modules.
Okay, so this is like saying I could build LLVM with 100 threads and now I cannot. So I get a smaller machine.
It will do the same. It will take the same time, because if parallelism is lower, then why do you use such huge machine? Like,
oh no, it's because the parallelism propagates, right? It's a transitive property that the other things are going to start first in the...
I don't know if it's managed really correctly, like if there are some parts that can start, if some other are waiting. I think Ninja is pretty good at this, but I don't know if CMake generates the right script for that.
Just a follow-up on the previous question. So basically, there is one more thing in the critical path here. It's loaded modules, which is also not free. So this also takes time. So once you compile this and then you load the AST, which also can be non-trivial in the time spent, because, well, if it contains a lot of templates, then those may be really slow to load.
Yeah, you remove the time to parse the file, but not the time to actually process it, because if you just import the AST, you just skip one step and not the others.
Hi, thanks for the talk. You talked about using Clang scan depths to capture the parts of the dependency graph. Do you do that for the whole project and merge that kind of monolithically? Or is it possible, like if you have a very large project, is it possible to run Clang scan depths only on the bits that you actually need?
So there is a property on targets to disable scanning if you really need to optimize your build. And also CMake will only scan files that has been marked as modules with file sets, or targets that consumes other targets that has modules.
Right, but if I have a huge project and it's entirely modularized, but I only want to build this part, or I only want to build this part, I still need to do the scan of the whole project. Is that right?
Yeah.
Okay, thanks.
Thank you, Alexy.